this topic. Yeah. So we're going to look at matrices this evening. Maybe we'll spend today and possibly Monday um, on the topic of matrices. It's rather wide, right? Um, Matrices is the plural of the word matrix, right? Excuse me. Uh-uh. Not to be confused with the movie, right? Matrix. What really is a matrix? A matrix basically is it's an array of numbers, right? It's an array of numbers, and you normally write them in a bracket. You have I'll just put some numbers, to so these are what we call rows. Rows. These are rows, and then these here are called columns, right? Columns. And in when matrices are applied to um, the business world and so you will see that these numbers can mean something. Like let me just give you an example. Right? As a matter of fact, I taught a course the other day, business mathematics, and there's a big chunk of the course that has to do with matrices, right? And you represent all kinds of production figures and so with matrices. So maybe okay, you're talking about all right, what Guyana producing gold. What else? What else? What else? Um, timber, timber, rice, right? And maybe, okay, we're talking about how much money they earned in, let's say, the year. Let's go from 2024, then you have 2023, then you got 2022, and you can actually put a figure here as to how much money was made, how much money was grossed, right? By gold, timber, rice, and so each year, right? And that's a matrix, right? It's an array of numbers, right? Where you can say, all right, you can in this case we let the columns be the various resources that Guyana produces, right? And down here you can probably have well the years, the years we call it fiscal year, right? So yes, matrices can represent real life data, and they can be very, very large matrices. Um, and they can, okay, thank you. Yeah, 1 second, please. Yeah, and they can be used to do some very complex calculations um, that can answer a lot of questions in the business world, business economics as well, right? Management and all of that. Maybe I'll find some nice examples that I used in that course and share it with you. It's not in your course. You are now learning the ABCs of matrices, right? So you don't want to get there yet. Good. So back to the basics of matrices, right? I want to go back there. So we talk about matrices having rows and columns. There's something called the dimension of a matrix, right? The dimensions of a matrix usually state, right, the dimension of a matrix is really a statement of the number of rows by number of columns, right? That's how you write the dimension of a matrix. Like this one we have, they have 2 rows and 3 columns. So you say it's a 2 by 3. That's how you say. You don't say 2 multiplied by 3. You say 2 by 3. It's a 2 by 3 matrix. Right? Good. So now that we got introduced to matrices, we want to talk about what we'll call matrix algebra. Matrix algebra. And here we can talk about the addition of matrix, the subtraction of matrix, right? I should use the plural, right? The addition of matrices, the subtraction of matrices, the multiplication of matrices. However, we're not going to, or there isn't anything like division of matrices. What you have is something called the inverse of a matrix. And we'll talk about that. Good. So let's start with addition and subtraction. Those are always the easier ones, right? Good. Let's say you have a matrix, all right. And you're adding 5, 1, 2, good, like that, right? When you add 2 matrices, you simply add corresponding elements, right? So you add this 5 and this 5, right? So it's equal to 5 and 5, 10, all right. Minus 1, and that 1 is 0. 2 and this minus 2, 0. 0 and that 5 is 5, right? So when you're adding matrices, you add corresponding elements. Now that should tell you something. If you're adding corresponding elements, then the 2 matrices that you're adding must be of the same order, right? That's another word for the dimension, right? The dimension must be the same, right? Or the 2 matrices that you're adding must have the same dimension. So like this one, it's a 2 by 2, and this other one is a 2 by 2 as well. So they have the same order, or the dimensions are the same. So you can add them. The same is true of subtraction, right? The same is true of subtraction. So let's say you have and you're subtracting. You notice the 2 matrices are of the same order. They are both 2 by 3s, right? This is a 2 by 3, and that's a 2 by 3, right? Same order, same dimension. And what we do, we subtract corresponding elements, right? So when we subtract, we get what? We can put the answer here. 4 minus 10 is minus 6. 3 minus 2 is 1. 1 minus 5 will give us 6. 6 minus 4 give you 2. Minus 1 minus 5 gives you minus 6. 4 minus 8 will give us 12. Right? And that's our answer there. Simple enough.
Yeah, simple.
When you add matrices, you add corresponding elements. When you subtract matrices, you subtract corresponding elements. And the fact that you have to add or subtract corresponding elements, the two matrices got to be the same dimension because they got to match up, right? You got to match up. The two of them got to be exactly the same dimension. So addition and subtraction is quite easy. However, multiplication and so might be a little more complicated. Right? Let me just do another problem involve addition and subtraction, because not all of them might be this straightforward. Look at this one. See this one? So you're not just asked simply to subtract the matrices. You actually have to solve some kind of problem that is within there, right? You want to find values of A, B, C, and D, right? So you can do your subtraction according to this here, A minus 4. All right, let's do the subtraction. So we're going to do this piece here. So A minus 4, you write A minus 4. 3 minus C. Oh, sorry, 3 minus C. Minus 1 minus D. Minus 1 minus D. And then B minus 5 now become B plus 5, right? All of this is equals to 5005, right? What is this thing doing here? Yes. Good. So from this now, let me see if I can take it up a little. Yeah. So A minus 4 equal 5, right? See that? This is equal to that. That implies that A equal 4. No, sorry. A equal 5 minus 5 plus 4. Yeah. A equal 5 plus 4, which is 9. You agree with that? You bring this over here. Let's go with the B. B plus 5 equal 5, right? This B and that's 5. So B plus 5 equal 5. That implies that B equals 0, not so? Hmm?
I'm trying to
Good.
follow, so
3 minus C equals 0. 3 minus C equals 0. That implies that C equal to 3. And then D minus 1 minus D equals 0. Minus 1 minus D equal to 0. That implies that, let's see, if you bring the D over here, you get D equal minus 1. right? So we got A, we got B, we got C, we got D, all the values. What they're simply saying is that if they're saying when you take this and subtract this, it's equal to that. So you do the subtraction, and if the two matrices are equal, then their corresponding elements got to be equal. Right? So when there's a little note you can take there, when two matrices are equal, their corresponding elements are equal as well. And from that now, that idea of corresponding elements being equal, you can equate one at a time and find the value of the unknowns, A, B, C, and D. Good. So let's turn our attention now to multiplication of matrices now. Right? So we start with what we call scalar multiplication. Right? Now what this simply means is if you have a matrix and you were to multiply by a number in front here, right? Very much like the distributive law. You just multiply everything in here by the 2, right? So you put 2 by 4, 2 by 3, 2 by 1, 2 by -1. That's simple as that, right? And you get what? 8, 6, 2, -2. That's very easy, right?
Looks so, sir.
Yeah. Very simple. When you have to
Yeah.
multiply by a number in front there, you just multiply everything inside by the number in front.
And that's it, sir? Nothing else?
That's it.
Okay.
No, matrix multiplication continues. This is only scalar multiplication.
Oh.
Gotta get complicated now. So now we're going to do general multiplication now. So hold on to your seats now. Okay. Let's say you have to multiply two matrices. 2, 1. Good. How do you do this now? Right? Well, you multiply rows by columns. So this is what you do. You multiply this row by this column, and that's what you will put here. Then you multiply this row by this column, and that's what you will put here. Then you multiply this row by the first column here, you put that here. And then you multiply this row by this column, and that's what you put here. Right? Let me do that. Let me do that again here. So, all right, 2, 1. So, okay, I said this row by this column. So you can do 2 by minus 1 plus 1 by 5. 1 by 5, right? So all of that you will simplify. Then this row by this column. So 2 by 2 plus 1 by 0. And this row by this column, 0 by minus 1 plus minus 1 by 5, right? If you want to put this in a bracket, no problem. And then this row by this column, so 0 by 2 plus minus 1 by 0, right? This row by this column. Oh, so we'll have to move it up. And we'll get what? We get 2 by minus 1 will give us minus 2 plus 5, so you get minus 3. All of this turns out to be 4. This is going to be 0. That's going to be minus 5. And that's going to be 0, right? Rows by columns. Now there is a condition before you can multiply. Before you can multiply two matrices, there's a condition to be met, right? And let me just specify that condition. Maybe you didn't see it. Digest this. Let me move it.
Yes, sir.
All right. So let me write out the condition. Two matrices, A and B, can be multiplied, only if the number of rows in A is equal to the number of, sorry, what did I say? Only if the number of columns, I got that wrong, columns in A is equal to the number of rows in B. Right? So in other words, if A here is A has dimension, I'm gonna write any word. M by N, B has to have dimension N by some other thing, right? It can be N by O. That sounds like not, no? All right, yeah. So the number of columns in the first must be equal to the number of rows in the second. And the result will be of dimension M by O. So that's a condition that got to be met. If that doesn't happen, you're going to end up with some awkwardness. I need to show you that maybe with an example.
Please
Right?
go back that piece now. A has a dimension of mn, and B has to be the has to have the dimension n times whatever the number is. So
Oh,
n is which
right.
one? N is the column or the row? Not m times n. The n is a column or a row.
N is the remember it's rows by column. The columns in the first one, A, the columns here got to equal to the rows here.
Sorry, is another.
Yeah, I'll show you what I'm saying there. And usually when two matrices can be multiplied, you will know because the arithmetic is not going to work out. I'll show you what I'm saying. Let me go back to the previous one. Right down here, this is a 2 by 2, and this is a 2 by 2. So this number equal that number. So yes, you can multiply. And the answer is this 2 by this 2. And you see that the answer is a 2 by 2, right? Let's try something like this. All right, watch it. Let's try a 2 by 3 and a 2 by 2. So here, this is not equal to that. So let's try it and see what happens. So 2 rows, all right, let's go with 2 rows and 3 columns. 1, 0, 1, 2, 1, 0, all right, times. Let's go with a 2 by 3. 1, 0, 0, 1. Good. So what would happen here if we try to multiply this? Remember, we have, okay, we got rows by columns. So that should go here. Rows by columns, that should go here. Rows by columns, we go there. And rows by column here, right? So what you see happening here, right? The rows by the column, you end up with a 2 by 2. So you get a 2 by 3 by a 2 by 2, and you end up with a 2 by 2. You see, so that can't work. This number and this number is not the same. Right? You just can't multiply two matrices where the number of columns here is not the same as the number of rows there. Right? What actually happened here is that you have lost. I guess you have to see it being applied. All right. You have to see. It's a bad thing when you let's go to application, right? Like let me go in geometry. Let me go into geometry. So let's say you have a triangle, and the vertices A, B, and C are what was it we had there? 1, you had 0 here, you had 1 there. Let's say 2, 0, 1 or something, right? Times something here, 1, 1, or 1, 0, 0, 1. Now, when you finish, you end up with a 2 by 2 matrix. You end up with a number there, a number there, a number there, a number there. So what have you done with the triangle? When you multiply it by this 2 by 2 matrix, the answer is meaningless, right? The answer is meaningless. What is this 2 by 2 matrix? It makes no sense. However, if I were to go back there and switch it around, watch here. If I take this and switch it around, I have 1, 0, 0, 1. And I multiply by 1, 0, 1, 2, 1, 0. Good. So let's say this is the vertices of a triangle. When you multiply this by this, this by this, this by this, you will end up with a, so watch here. This is a 2 by 2, and this is a 2 by 3. So this number and this number is correct. It's the same. And our answer is a 2 by 3. So you'll get a number there, a number there, a number there, a number here, a number here, a number here. So you do have a 2 by 3 at the end. And this is meaningful. This might very well be like what you call a transformation, right? You all would have to see that later on in the weeks to come. Maybe next week we'll touch on this. Where you do a transformation, you take a matrix and you multiply by the vortices of, let's say, a triangle. And your answer is another triangle, right? In that you did a transformation. So let me show you that in the so like when you, I don't know if any one of you, when you did CXC, you have a triangle here, A, B, C, you know, and you do some kind of maybe a rotation. There's a matrix that will do that rotation for you. So this triangle is rotated and you end up with, let's say you end up still over here, and you end up with A, B, C, right? So if you did a transformation by multiplying it, okay, you take the A, B, and C, numbers here, numbers here, numbers here, numbers here, and you multiply it by some transformation, right? A transformation represented by a matrix, right? Let's say call this a rotation matrix, R. Your answer has to have three. You have to have A, B, and C. You have to have three vortices. You can't have a 2 by 2 as the answer, right? You can't have that because if you take a triangle and transform it, you have to end up back with another triangle. So you can't have a 2 by 2 matrix. A 2 by 2 matrix only have, okay, a point there, here, here. So this is a point and this is a point, right? So it wouldn't work. It doesn't obey the rules, right? But now if you don't get all of this, it doesn't matter. Just memorize the rules. You got to study, as I said, matrix. You are now learning. You just awakening to something named matrix, right? As you get into the application of matrix, then you will see that, oh, the rules make sense, because if I were to put, the 2 by 2 behind it, the 2 by 3, that will produce something that is meaningless, right? But if I put it 2 by 2 in front, which is the transformation, and put the vortices of a triangle behind, the answer will give me the vortices of a triangle as well, right? But you'll get to that. It will take a while. You're not ready for that, right? You're not ready for that. And you're going to learn a lot of things, like okay, if you have a matrix, let's say A is equal to the matrix 1, 1, 2, 1, and B equal 2, 1, 0, 2. Let's say that, right? You will find out that AB is not equal to BA, right? In a lot of cases, in most cases, that's not true. Unlike other in algebra, when you multiply 2 by 3 and 3 by 2, you get the same answer. But you will find here that AB is not equal to BA. Sometimes, all right, let's say this is not B. B is, let's say this is a 2 by 2, 2 by 2, and B turns out to be a 2 by 3. Then you will see that AB, you can have AB, but you can't have BA because BA break the rules. BA is a 2 by 3 by a 2 by 2. This can't work, right? But AB can work because 2 by 2 and 2 by 3, these two numbers, sorry, 2 by 2, this 2 and this 2 is the same, so it can multiply. But BA, you have a 2 by 3 by a 2 by 2. This number and this number are not the same, and therefore you can't multiply it. See? I don't mean this is not a 2 by 3, right? I'm just saying that if B turns out to be a 2 by 3, right? But generally in matrix multiplication, AB is not equal to BA. It's not equal to, right? You're going to learn a whole lot more about matrix multiplication, right? We also, I mentioned to you, we're going to do something called the inverse. The inverse uh, of a matrix, right? And we are going to stick with a 2 by 2 matrix, right? The inverse of a 2 by 2 matrix, right? And what the inverse of a matrix is really, that if you take, if A is a matrix, right? And A inverse is the inverse of A, or A to the minus 1 is the inverse of A, then you will find that A times A inverse is equals to what we refer to as the unit matrix, right? And if you're dealing with a 2 by 2 matrix, the unit matrix, the 2 by 2 unit matrix is this matrix 1 0 0 1, right? So when you take a matrix, a 2 by 2, and you multiply it by its inverse, you get what we call the unit matrix. How do you find the inverse of a 2 by 2 matrix? That's what we're concerned with. How do you do it? How do you find it? So if A is equals to A, B, C, D, right? Then A inverse is equals to 1 over AD minus BC times DA. Switch around these two and you change the sign of these, right? And this here, let me explain what are these. AD minus BC is called the determinant of the matrix A. Why you call it the determinant is that it tells you whether the matrix has an inverse. Because if AD minus BC, if AD minus BC equals 0, well, you have 1 over 0, which is undefined, then A does not have an inverse and is said to be a singular matrix, right? So if AB minus BC, that the determinant there is 0, the matrix doesn't have an inverse, right? And this part here, right? When you take A, B, C, D and rearrange it like this, change up the sign. This is what we call the adjoint of A, right? The adjoint of A. Ready for an example?
Yeah, yeah.
All right, let's do that. Let's do that. So let's say, all right, you have a matrix A equal to 5, 3, 3, 2. Let's say you have that. You have to find A inverse, right? So A inverse is simply 1 over AD, which is 10, 5 minus multiply by 2, subtract 3 by 3 times, okay? So we'll switch these two up, change the sign here and here, right? So all of this turns out to be 1. So your answer is 2 minus 3 minus 3, 5, right? And to check it, remember I told you when you multiply this by this, you should get 1001. Let's see. Let's see if it's true. So let's see. We can. Let me check it. Multiply this by this, right? So 5, 3, 3, 2 times 2 minus 3 minus 3, 5, right? Let's multiply. Let's multiply. So this row by this column, 5 times 2 is 10 minus, sorry, what am I doing? Plus 5 by 5 um, by 2 is 10 plus 3 by 3 is 9. You get 1, right? And you add it to 5 by minus 3 is minus 15 plus 3 by 5 is 15. You get 0, right? And you go with this row by this column. 3 by 2 is 6. 2 by 3 minus 3 is also minus 6. So add the 2 together, you get 0. Then 3 by minus 3, you get minus 9 plus 2 by 5 is 10. So you add them, you get 1. You get 1001. You do have the unit matrix. So we were right. We did get the right inverse.
Magical.
Yes. And I'll tell you what, matrix algebra is so reliable that they use it a whole lot in computer programming, right? Because a matrix, we can code all kinds of data in the form of a matrix. And you can do all kinds of calculation with that data in matrix form. And the matrix arithmetic is never wrong. Right? Remember, in computer programming, the program is counting that the arithmetic is going to work out. Right? And if the arithmetic isn't working out, you corrupt the whole program and crash it. Good. So you want us to take a little break there, and then we come back and I'll show you how we can use this whole idea of the inverse to solve what we call simultaneous equations. Remember, I think we did simultaneous equation. So you're going to see a matrix method to solve it now. Right?
Okay, sir.
Good. So let's take a few minutes. And we come back at 6:30.
Yeah, sir. I
Yes, sir.
Good. So as I said, we're going to do a little application of, well, how do you use this whole inverse thing to, do something else in mathematics. And what we're going to do, we're going to use it to solve what we call a simultaneous equation, right? So let's say we want to solve, let's go with 5x plus 3y equal 4 and 3x plus 2y equal 2, So what we can do with this equation, we can write it in this form. We can write it like this. We can write it like 5, we take the coefficients, right? 5, 3, 3, 2. And we write it times xy will be equal to 4, 2, right? Write it like that. So we're gonna name A, we're gonna name this A, we'll name this X, we can probably call this B, right? So if we want to take this, basically this is the equation AX equal B. So when we take the A over here, we don't divide. Remember, there's no division in matrix algebra, right? So when we take the A over there, the A becomes A inverse, right? So in order, remember, we want to find X and Y, right? We want to find this big X here. So what you're seeing here is that we need then to find the inverse of A, right? The inverse of this matrix here. So that's what we're going to do, right? So let's see what happens. Let's do that. So the inverse of A, right? So A equal 5, 3, 3, 2. A inverse is equals to 1 over, oh, we get a nice 5 2's 10 minus 9 is 1. All right. 10 minus, all right, what are we here? 10, let me write out the whole thing so you know what I'm doing. 5 by 2 minus
Right.
3
I
by
was
2,
just going to
right?
tell you that, sir.
Times, okay, switch this 2 up, 2, 5, minus 3, minus 3. It's the same thing that we used before, right? We found it before, good. So A inverse is, well, this is 1, right? 2 minus 3 minus 3, 5, good. So according to this here, X, right? Remember we said X equal A inverse times B, so XY is equals to A inverse, which is this, 2 minus 3 minus 3, 5, times B, which is 4, 2. So let's see, we'll multiply that and see what we'll get. So XY is equal, so let's multiply. 2 by 4, 2 by 4 plus minus 3 by 2 minus 3 by 4 plus 5 by 2. So we get what? 2 by 4 is 8. 8 minus 6 is 2. Minus 3 by 4 is minus 12 plus 10. We are minus 2. So X equal to Y equal minus 2. Right? And you can check it to see. Is that going to be right? Yeah, that's right. If you put X equal, look here. If you put X equal 2 there, 5 2 is 10 plus 3 by minus 2 is minus 6, right? So 10 minus 6 will give you 4. And 3 by 2 is 6 plus 2 by minus 2 is minus 4. So 6 minus 4 equal 2.
So I'll do a next one.
Yeah, all right, we'll do another one. I'll do one where the numbers aren't so nice.
Wow, ways.
Let's do another. Good. So, all right, let's go with, all right. 2x plus 3y 8, all right, 3x minus right. Good. So what we're going to do, we're going to write this in matrix form. So you get 2, 3, 3 minus 2 times x, y, 8, 4, right? And we'll name this A, we'll name this X, and we'll name this B, right? So we know that X is equals to A inverse times B. So we need to find the inverse of this, right? So A is 2, 3, 3 minus 2. A inverse would be equal to 1 over 2 by minus 2. Give you R, we put it 2 by minus 2 minus 3 by 3 is 9, right? And then we switch around these two, change the sign of these two, right? What do we get there? We get 1 over 2 minus 4 minus 9
Minus 4.
minus 13. Right? So the number is nice. It's ugly. My advice to you is don't multiply this into this. You'll end up with some horrible fractions. Right? Do this instead. So we know from this here, right? From this one, x is equals to A inverse, which is this 1 over 13 minus 2 minus 3 minus 3, 2 times 8, 4, right? So multiply this by this, and you get some nice numbers. And then you multiply by that. Let's see. All right? So multiply this by this. You get, okay, leave the minus. Minus 2 by minus 8. Minus 2 by 8, sorry. Plus minus 3 by 4. And multiply this by this. Minus 3 by 8 plus 2 by 4, right? You end up with what? Let's see. This is minus 16. Oh, this was supposed to be a minus 1 over minus 13. Huh? Yeah. Oh gosh, what happened there? What happened there? What happened there? This was supposed to be a minus here, right? Minus, minus, right?
Yes, sir.
Yeah, we didn't. Yeah. So all of this is minus 16 and 12 is how much? Minus 12 is how much? Is that right? Minus 16 minus 12 is how much? 16 and 10. Yeah, minus 12. I wonder if man, I think I use a horrible, a wrong number. Let me just see back something here. Oh my, I use a horrible number there. Yeah. All right, you'll end up with a horrible number. It's going to be hard to check, right? So you get, this is minus 28, and this is going to be what? Minus 18 plus 8. So it will be 10, right? And then you multiply by the minus 13 there, right? So you end up with 28 over 13 and 10 minus 10 over 13, right? You can actually write this as a mixed number if you want. You can leave it like that. Yeah, I use the horrible numbers, so not all the time it will come out like the force example. Sometimes you'll get some terrible looking values, right? Yeah, my intention here wasn't to I used the wrong number here. Down here I was supposed to have this is supposed to be minus 1. If I'm to do it back with that, this was supposed to be, what did I do? It's supposed to be minus 1, right? So you're supposed to get some nice numbers when you finish. Anyway, leave it like that. What did I have there? 4? 4? Oh, leave 4. You end up with some horrible numbers, but yeah, that is the answer. Not always will you get nice looking answers, right? But the procedure is the same. The procedure is the same. You just follow the procedure and it always come up. It will always come up. Good. So I didn't want to do another subtopic. No, I wanted to stop there. Because if I introduce transformation now, I think it's going to be too much for you. So we did the addition, we did subtraction, we did multiplication, we looked at the inverse, and we used the inverse to solve simultaneous equations. Right? So I think that's sufficient for one afternoon. Right? Good. So we gonna pause there.
Okay, sir.